and move on to the last presentation of this session, presentation by Dr. Didier Haas. He's an ex-advisor for nuclear safety and security in European Commission, and he's going to talk to us on overview of European experience with thorium fuels. Dr. Haas, please.
Thank you. Thank you very much.
Oh, somebody else is speaking.
C'est ça, ok. C'est pas ça. C'est pas celle-là. C'est celle. Non. Haas. Ici. Ouais. Okay. Good morning, still good morning to everybody, and thank you very much for the organizer to have invited me to this important conference. I'm very happy about that. Effectively, I'm retired from the European Commission. In fact, I spent 25 years in the industry before joining the European Commission, and I worked during these 25 years on MOX fuel. So not directly thorium MOX, but uranium MOX, in Belgium Nuclear in Belgium. And I worked in the engineering, design, and fabrication of fast reactor and light water reactor MOX fuel. Then I moved to Karlsruhe, the Institute for Transuranium in Karlsruhe. And there, my job was the department to lead the department of fuel fabrication. And we developed a minor actinide laboratory for transmutation fuels, and we also fabricated fuel with thorium. So my specialty is really linked to the fuel fabrication and irradiation in reactor experiments. But today it will not be a political speech, it's technical about the program and the project that have been performed in Europe on the thorium. Some reference I have taken in order to prepare this presentation, what we call the Lung report. It's a Euratom report written by Dr. Lung in '97. The fuel conference in Paris, the Thor Energy 2010, IEA, of course, we have heard about the important work done there. A GIF position paper on thorium, on the use of thorium in the nuclear fuel in 2010. The SNETP, European, I will explain, Research and Innovation Agenda in 2013. And an annex on thorium in 2011. And of course, published results and some personal views and personal communication. First, European research on thorium in general. Then 3 topics: thorium in high temperature reactors, thorium oxide fuel behavior for light water reactors, and molten salt reactors. These are the 3 topics specifically studied in the research programs of Europe. So this is the known figure on the Sustainable Nuclear Energy Technology Platform with the 3 balls, one related to light water reactor fuel research, another to the cogeneration process, heat production, high temperature reactors, and the third on sustainability, fast reactors. The thorium and molten salt and these activities are in the middle, embedded as a horizontal projects. There are many members in this platform, 117 today, and in red, just recent application of Weinberg Foundation UK and Thor EA from UK, who both are promoting, of course, the thorium research. Today, major stakeholders in Europe have not put this today as a first priority, and therefore the research agenda have been, let's say, mainly devoted to the 3 bullets shown in this figure. So concerning now the European R&D roadmap. So the roadmap produced by this platform. Here are the, let's say, the parts devoted to thorium. It was produced in 2011. And the main highlights are the following. Very briefly, I will, let's say, give more weight on the 3 points in yellow, as I mentioned in the introduction. For light water reactors, it's considered that evolutionary development are favored with the use of plutonium as seed material in order to have a better conversion. So use the thorium and plutonium in order to save uranium, of course. In the document, it's considered that breeding certainly would need a new reactor technology, and this was already said today, of course. In the heavy water reactors, high conversion ratio are achievable. It is not studied in Europe. There are some heavy water reactors in Romania, but this is not a major emphasis. In the case of HTR, there were reactors operated in Europe, and we will see that, of course, as was mentioned already before, let's say the breeding cycle with thorium is achievable in high temperature reactor. Concerning fast reactor, it is considered that breeding is possible, of course, with thorium, but with long doubling times, and there it is considered to be better to use the uranium-plutonium cycle. However, in the case of, it's also a fast reactor, advantage for ADS, of course, it could be certainly advantageous to use thorium, because in this case, with the high energy spectrum, the thorium-232 is fissionable by himself, and of course, the capture can produce the uranium-233. So this is a possible application in fast reactor. Then, but again, we have no research project which have been undertaken, financed by the European Commission in this area until now. It can change, of course, in the future. Next one is molten salt reactor. There are programs. Breeding may be achieved over a wide range of neutron energies. We have seen the graph 2 times, in fact, today. And this is clear, is a big advantage. And it is, of course, a long-term development option. I will come back on that. Finally, plutonium burning for those countries depend on the strategy and so forth. But those countries wanting to have a quick burning of plutonium, a thorium matrix has been proposed for burning this plutonium in light water reactors. And this is the 3rd subject I will mention. The challenges are the same as presented before: reprocessing, remote fuel fabrication in case of solid fuel. So in Europe, the projects have started a long time ago, in the 60s to 80s, with quite limited, we can say, although it's important, experimental work on thorium use in high-temperature reactors. It was already shown in the graph. Here I speak only on the European project, the Dragon project, ATR project, THER in Germany, with thorium, uranium carbide, and oxide fuels. I will show you in the next. It's not there. Yes. This is an abstract of the Lung report, but in fact it's a table coming from an old 1980 IEA report, and it shows the line on the fuel kernel composition: thorium, uranium dicarbide, thorium carbide, oxide. So both type of fuel have been loaded in these reactors, and these experiments were very successful. There was a very good results, high burn-up achieved, and no real big problem with the use of the thorium. Yes. Of course, there are limitations. If you use in a high-temperature reactor, let's say, a one-screw strategy, you need, of course, to have a very high enrichment, and it can be even, okay, today it would not be possible anymore, above the 20% limit. And if you use the 20% limit, it is very expensive to enrich the material up to this value, and so the cycle, the fuel cycle, may cost a lot of money. In the case of the reprocessing scheme, the closed cycle. It is technically feasible and possible, of course, to reprocess anything. Chemists can do anything, but it will also be difficult technically and quite expensive. So these are the limitation in the use of the thorium in the VHDR. Okay, today the very high temperature reactor is one of the 6 systems of the GIF in the R&D systems, and many of the GIF participants are also participating in this VHDR system, including Europe through the Euratom participation. Of course, from a European point of view today, it is very difficult to get industrial interest in the HDR. Although there is a very big potential of heat production in industrial application, but the problem is who is the customer? Heat industry should be the customer, and they are reluctant to take this risk, of course. So if the country, the government are not backing these programs, it's very difficult to get this program going on. So now this is about the thorium in high temperature reactor. Now a second is thorium oxide as what one could call a quasi-inert matrix. You know that studies have been done in partitioning and transportation using inert matrix. Inert matrix mean plutonium oxide or minor actinide are mixed with something that has absolutely no uranium or any kind of actinide as a matrix. So, for example, we could imagine zirconium oxide or MgO or a metal like molybdenum metal. It has been done in the minor actinide laboratory. It has been irradiated. But another matrix which is closer to the U2 is, of course, thorium oxide. So this was a selection in order to ease the process of the licensing of this material if it's used in the future, as compared to fully inert matrices, which are very different from U2. So thorium, moreover, of course, you know, is a very stable ceramic, and so it is stable, which is important during the reactor operation. It will not give different phase and complication in the use, but also in the disposal for the waste management. It's very important, and I will show you leaching test, corrosion test results on the thorium, and it is clear. It's difficult to reprocess, but the advantage is it is also difficult to dissolve, and so it's very stable. So it has been, as I said, contemplated, chosen to incinerate separated plutonium in light water reactors in a fertile matrix, and also for inert matrix for minor actinide burning in a kind of targets, as I explained. So the thorium matrix produces no new plutonium and is fertile as required to keep reactivity in light water reactors. So it presents this advantage. In-reactor properties are equivalent or even better. I will come back on that if one considers the thermal behavior and the stability of uranium MOX compared to uranium MOX. Thermal diffusivity measurements on unirradiated thorium MOX have been performed at the Joint Research Center of the European Commission, ITU, and it's better than uranium MOX. Let's come back a little bit. The thorium cycle project for PNT and ADS was started in '98. And you can see, we have no time to go through all the boxes there, but there is one box there at the beginning, at the top right, on the transportation fuels. And in this transportation fuel, at that time, thorium was considered as one of the candidate transportation fuels. All these boxes, green boxes, were networked into coordination network called ADOPT, and the discussion held at that time led to the definition of a new project, a very big project, 32 million, which is called Eurotrans. And Eurotrans is, of course, the very important basis for the design of the ADS. This was the major aim at that time in the next framework program of the European Commission, Eurotrans. the thorium was, as such, was not anymore considered in the fuel box DM3 AFTRA. It was only considered to use inert matrix fuel in this frame. But in parallel to the Euratom projects, other projects were launched here, not part of Euratrans, but parallel to that, and they were including thorium fuels like LWR Deputy project. So altogether, in Europe, in the last 10 to 13 years, experimental work has been done on thorium-plutonium oxide in light water reactor, for testing light water reactor type fuel, in 3 reactors, in the HFR material test reactor in Petten, in the BR2 in Mol, which is also a material test reactor, with instrumented and non-instrumented PWR fuels. And then in a commercial reactor. So we produced fuel, by the way, in the ITU when I was there. So it was a pleasure to fabricate this, and I will come back on that. The fuel was loaded in the KVO Oberigheim pressurized water reactor with the cooperation of Siemens at that time for the design of the fuel. Post-irradiation examination, of course, were made in various laboratories in Europe, ITU. So the thorium MOX, this figure has been shown already. Of course, it's similar to uranium MOX. It behaves equally, as we can say, and there has been several publications on the results of this examination. I would like to stress one aspect. It's the thermal behavior, because it's very important, because it leads to the calculation of the central temperature, and the central temperature in a light water reactor is the major parameter for almost all the important in-pile properties of the fuel. So it's important to keep this fuel temperature as low as possible. Here, this graph shows you a lot of lines. Just to take out of this is the diffusivity measurements performed in ITU, and not only in ITU and other laboratories, and shows that of course, going from PO2 to thorium oxide, you have a much better thermal conductivity with increasing the ratio of thorium. So now this is the same, but it shows 2 graphs. One graph is on the right side, a little bit the same as before, but thermal conductivity. And as a summary, at 1000 degree Kelvin, the thermal conductivity of uranium MOX will be between 3 and 3.5, thorium MOX above 4. This gives you the range of improvement of the thorium. But I have another remark. It is on the left side. This is only considering MOX fuel, uranium, plutonium. And the curves can be different also very much, not very much, but okay, in a range of at least 10%. If you consider MOX, depending on the way you have fabricated the MOX fuel, heterogeneous MOX or homogeneous MOX. So I would like to mention something. It is very important to consider the fabrication process before you decide that one fuel is better than another from a point of view of the fission gas release, for example. So the thorium MOX, which was manufactured in the KVO experiment, is manufactured by a homogeneous method, by coming from a liquid and mixture of the thorium and uranium in a liquid phase, and then producing finally pellets by a kind of semi-sol gel process. It is different if you manufacture a MOX industrially, where you have a concentrate of high plutonium content at some plates in the pellet. It will differ. So it's important to get right results before you make the licensing. So we are not so far yet. Here it's a figure coming from the SEK MOL in the LWR Deputy experiment, where the pins, thorium pins, were instrumented, so the measurement of the central temperature was possible. In the light gray, you see the measurements value and the different codes for comparison. And bon, it shows only that nothing is perfect, and the codes, if they are applied before you know the results, they don't show very good results, but that's quite normal. You have to have more data and adapt your code in order to get the right results. So the work is certainly not finished before it's possible to license the fuel. Another point I mentioned is leaching. So many data here. I don't go through. Source is the experiment performed in ITU, also at the Joint Research Center in Karlsruhe, Rondinella. And just the 3 points below show particular thorium point. And of course, the corrosion rate is much lower in this case, as expected. Another project financed by European Commission is the so-called SKIN project. It's still going on, and it's a comparison of solubility values of different elements in red on all the curves. The example is taken as a SKB, Swedish spent fuel repository, with different graphs corresponding to different compartments of bentonite granite. And the calculations show that every time in each compartment, of course, again, it's expectable. It can be expected that the red curves with the thorium is the lowest curve in rate of dissolution. So, this was it's a kind of conclusion for this thorium-plutonium research programs made by the people who have made the research. And ThEC, as I said, is one of those. No showstoppers identified for thorium, certainly not. It presents several advantages over uranium, like a better thermal conductivity, improved chemical stability, indication for improved reactivity margin for full core PWR. Okay, this certainly needs further conclusion. Next step, however, and as I mentioned it, improving the fuel manufacturing technology is necessary. Since the scoping studies used non-industrial and non-industrializable methods. You cannot suddenly make your thorium fuel with a liquid sol gel method from one day to the other. It's not used. So I think thorium, if it's used commercially, must go through a mixture of powder process, and this needs to be tested before. Yes. Final subject is the use of thorium in molten fuel reactor. It has been covered quite a lot by, much better than me, by most previous speakers. Here we speak about the R&D program on the European scale. One should also not forget that European scale research in fission is not big, in fact, in terms of money. It represents about 50 to 60 million euro per year of research money on all these projects, not only on thorium, on all the projects. Let's say that all the money of the European Commission in the research, nuclear research, goes into fission. You know that. Anyway, molten salt thorium cycle can achieve a higher conversion ratio than the uranium plutonium. This is clear. The second point is important. In molten salt, the fuel is moving, so the fuel doesn't stay for a long time in the same place in the core, and so you have less time for absorption of the neutron by the protactinium-233, which is a byproduct, decay product between the thorium-232 and uranium-233. So this is a quite big advantage. Of course, continuous reprocessing avoids the problem that we have reprocessing the thorium fuel, and also avoids the fabrication of thorium fuel. So these are, in a nutshell, very simply, the big advantage. So many programs have been, not with huge budget, but continuous, let's say, program. By the way, with a quite good cooperation with a Russian researcher, different programs, and certainly there will be other papers presenting this in detail. Today, the program going on is the EVOR program, the thorium being nuclear fuel, the nuclear fuel, and with the principle of using a fast reactor core, molten salt reactor core. Here it is. MSFR concept is a French concept. It will be certainly presented, I think, the day after tomorrow. In this fuel, the fluoride of thorium, uranium mixture in the design of this core. Again, because I let's say speak a little bit more on the contribution also of the European Commission, not in terms of money here, in terms of laboratory work at the Joint Research Center in Karlsruhe. Again, a lot of work is done to let's say develop a database, the database for the molten salt systems. And a lot of these have already been assessed, many of them experimentally, and other parts are made theoretically based on some models. So it's a quite steady work that is been doing. So I want to conclude. Several EC, European Commission projects on thorium MOX fuels, mainly for light water reactors. There is no project in the R&D of the EC for a fast reactor, using thorium as a quasi-inert matrix to burn plutonium and possibly minor actinides. Second is thorium salts as a fuel for a molten salt reactor. And the SRIA published in 2013, this year, the conclusion of the strategic research and innovation agenda of the platform I mentioned, recognize significant long-term potentialities and also the challenge to make industrial implementation. This is clear. I would like finally to thank you for your attention, and also Michel Hugon and Roger Garbil of the EC, the DG RTD. They are managing the research project in Brussels. And also Rondinella Steikus Sommers in ITU. They are working with the laboratories, which I mentioned, and also Mark Verwer from SEK, because I work together to prepare this presentation. Thank you very much.
Thank you for your presentation on the programs in European Union. Any questions on this? Yes, please.
Thank you. Thank you for your presentation. You didn't talk about corrosion. My understanding is from the Oak Ridge, when they, after the 5 years at Oak Ridge, they identified the corrosion issue. My understanding is the EU had put together a budget for R&D looking at those corrosion issues. It didn't seem to be mentioned by you. Does that come from a different area? Would you comment, please?
You mean, sorry, because I think... You mean the corrosion. When I spoke about this graph on leaching, this is in fact corrosion. Corrosion of the thorium oxide.
Then you did cover it. Then I
yeah, sorry, maybe too quickly, but this is this graph, which presents a big, here, this is more based on calculation. These are dissolution results showing the red curve, the thorium oxide much better and corroding much less than the other. And these are experimental data from the ITU in Karlsruhe, showing many data, and with the most interesting, with the very low values of corrosion. Okay, I called them leaching test, but it's corrosion.
Okay, so with this, I think we're really running, maybe last one, yes.
My question is about the diffusivity. The diffusion coefficient of thorium should be less than the others. So I have not understood the graph. What is the advantage you were showing with thorium, with diffusivity?
No, so in fact, what I show...
The graph just before.
Maybe this one, because this one shows you the thermal conductivity.
No, this is the thermal conductivity.
And
the previous one.
Yes, but the thermal diffusivity, this is the measurement. Yes. And when you multiply by the heat capacity, you get the thermal conductivity. So it's similar. It's the same.
Oh, yes, It is not the self-diffusion
It's not the same value, but it's the same tendency.
Thank you.
Yes.
Well, I think we should stop here. We return our thanks to you for a wonderful presentation.